لا ما بستخدمش هرمون بس القلب شغال.
ما هو ساعات القلب بيعلق برضه، نشوف له بطاريه. لازم نشوف
مش مشكلة.
شوف له بطاريه يعني.
طيب ابتدي نراجع بسرعة حاجات المرات اللي فاتت قبل ما الناس تيجي. So basically we start احنا ابتدينا نسمع الفكرة كمان يجي بالعربي شوية. فابتدينا بالمعادلة البسيطة جدا دي بتاعت basically قلنا زي طوبة بتترمي من فوق، بس طبعا لما بتترمي من فوق جامد الراديوس بيتغير. فطوبة عادية الراديوس عشان الأرض كبيرة قوي مش هيفرق كتير قوي لو تترمي حتة صغيرة، لكن يعني almost to the escape velocity. We integrated this sort of equation وطلعنا energy integral, the constant of motion اللي هي الانرجي عشان potential does not depend on time. This is like a potential energy, the kinetic energy بتاعت السيستم بتاعنا. وعملنا له rescaling coordinates وشلنا الماس حطينا density, it's homogeneous density at any given time. And we found there's a constant لأي sphere with a scale factor A of t. Okay? For any sphere, and there's a scale factor A of t, and there's a constant for all spheres كنا عايزين ندور عليه. كان عندنا مشكلتين. الكونستنت ده أولا مش عارفين هو إيه عشان الديريفيشن بتاعتنا النيوتونيان بسيطة جدا. what do we do if we have relativistic things؟ دي طبعا زي قلنا طوبة أو ماتر، يعني حاجات عادية من ليها ماس، بس في حاجات ملهاش ماس بس they have gravitational mass زي الفوتونز. they don't have mass but they contribute to gravity عشان عندهم momentum. in relativity momentum matters as we know from special relativity, and we obtain this complicated energy momentum tensor. Some of it is simply the stress tensor of hydrodynamics, and parts of it are the relativistic time parts, which are relativistic, because relativity is for dimension. There's a time components. The space components are simply the stuff, at least for normal system, regular systems made of particles, it's just the hydrodynamics test tensor of fluids, okay? And because our situation was very simple, we said that there's only pressure because of isotropy, really, and homogeneity. There's only pressure that contributes, which are the VI terms, V squared, XX, VY, VZ. These are the isotropic terms of the momentum. And so on. So they're the only ones that contribute, and we call this pressure from hydrodynamics. We'll call it pressure here, and we said, and we add the three pressures, Vxx, we are connected to the Pxx and Pyy, or in terms of momenta, or if you do rho V squares, then Vxx, Vx squared, and so on. In the three spatial coordinates. And there's the density, and this is divided by c squared, so we said that this is inherently relativistic. Then we did also a very simplified thing of divergence of the stress tensor, which in our case is very simple, and simply the first law of hydrodynamics, of thermodynamics for an adiabatic system with ds equals 0. No entropy changes, no friction and things. You can't have any friction in systems that are isotropic homogeneous because there's no shearing or bulk flows and things like that. So you can't really have that. And we, to get, let's say, the equivalent of an energy integral, we use this energy equation for the process of expansion. What happens to our fluid if it's photons or particles or whatever it is, it follows these continuity equation to what happens to its energy and pressure when we do work on it by expanding the universe or contracting it if it's a contracting universe. Okay, and we got this equation again. You could have, by the way, started from this equation and used this one to get this one. If you're not completely convinced of why I put the 3p there, or not, why not something else? You can try as an exercise getting our Newtonian equation, energy equation, energy integral, and put it into this continuity equation and go there. Because they're dependent on each other, the three of them. Okay? They're not independent. Okay, so then we want to see this, what this thing means, this constant of motion, this integral of motion, constant of motion. And for that purpose, we started wanting to do metrics and things like that. And we said because of homogeneity and isotropy and so on, we can slice the space into equal time thingies, global time, for observers co-moving with this thing, with the expansion. And this describes the expansion. And this describes a line element, which could be flat, could be positively curved like a hypersphere, like a sphere in 3 dimensions. And the normal sphere is a 2-sphere, okay? One sphere is a circle, and this is a 3-sphere. Or it could be hyperbolic, negative. It can be, or it can be, of course, flat. Can't be anything else, because otherwise you'd need to, the curvature would need to change from direction to direction or from place to place. And in that case, you wouldn't have homogeneity in isotropy. So we did this exercise here, and we said there are 3 possible cases. This is for triangles that are more than 180 degrees when you have on a sphere, and this is for triangles that are less, and these are flat triangles. This is how he does, one of the ways you can differentiate between curved spaces. And, but of course, you cannot measure triangles of this sort in the sky really on cosmological scales, at least not yet. So how do we determine which space we are in? We cannot do it this way, by measuring triangles like that, at least not to my knowledge. Okay, so we needed to put all the stuff in our in the GR equation, which so you had this is your metric. If you k equals 0, this is just circle coordinates with a Minkowski, but with spherical coordinates. بتقولوا بيقولوا انا وقعت واحده قبل كده مسافه اقل وباظت. So there we go. And this is our metric. This is our metric tensor connected to a diagonal matrix with these things in the diagonal. This is corresponding to that, and this is this, and so on. And these are Einstein equations, which basically depend on the Ricci tensor and its contraction and this metric. So if I know the metric, and the Ricci tensor is like derivatives of this thing, so in principle I can calculate it, and then I start getting my dynamics from the time term, which in Newtonian we have 2 equations, one dynamic and one for gravity. Here they're together because it's a space-time. Okay. So this is my dynamic, and this is my spatial thing, and this turns out to be a Gaussian curvature, or related to it, multiplied by the metric. It's a Gaussian curvature. Because that's the only thing, it's one dimension, one Gaussian curvature, not different ones, and it's a constant because of homogeneity, and only one curvature because of isotropy, not many of them. And then this is my energy momentum tensor. One of it is the Newtonian thing, and then there is the pressure multiplied by this thing. There's different coordinates and conventions, but that's one of them. Okay? Okay, so I find out that my Newtonian equation becomes that. So this constant is like related to the curvature of the universe. And you can get also the acceleration equation from GR. I didn't write it here because it wouldn't be too many equations. And from the divergence of the stress tensor, you can get the third one that we did from the first law of thermodynamics. The three of them are not dependent. They're not independent. Okay? As in the Newtonian case, they're not really. One of them was an integral of another, and the third one was from thermodynamics, and you could, do two or three of them. It's similar, at least in this level. Okay, but we said, how do we determine our geometry of the universe? Is it flat? Is it curved? Is it positive or negative curvature, and so on? So we said we do this through the Hubble parameter and the density. So if we can measure the Hubble parameter and the density well, we can know the K, the curvature. Okay? So the Hubble parameter can be measured locally. There are different ways we'll discuss after tomorrow from the CMB and so on, but locally, it's CMB is because of my great background, but locally you measure it basically by plotting redshifts against distances and taking the slope. Of course, professionals would take higher order corrections. There's things called the deceleration parameter and the jerk parameter. They expand to higher order, but this is in the linear local approximation. Okay? So, but we don't know rho naught, and it turns out that rho naught is quite exotic. Okay? So we need to solve our Friedman equation. Okay, this one. This is the main one we're interested in from now on. So first of all, we need rho as a function of A so that we can solve this thing. So again, intuitively for matter it's 1 over minus A cubed, and for radiation A to the 4 because of the redshifting. And for cosmological constant, if you don't believe me, you can put it again in our continuity equation and you'll get that for the different equations of state. Matter is 0. Cosmological constant is minus rho. This is minus 1. And radiation is a third. And as I said last time, you get matter domination now. Radiation domination in the very beginning, let's say, so to speak, and matter domination in the middle, and then the cosmological constant starts to dominate recently. Could be different from a cosmological constant, but other sorts of dark energy, but for our purposes, it's a cosmological constant, okay? We have at least. And you can do it for flat universe, different cases. Let's say we only have radiation dominated early, or matter, or only a cosmological constant, and you get these three different solutions to that. I think this should be completely clear. Okay? It's very easy. You solve this equation. For example, if rho is constant, it's obvious that this is going to be an explanation. Okay? Right? Now, but we need to relate all that to observables. We're not there yet. So we don't observe A, and we don't observe T either, the cosmic time. We just have one here, and we can't make a map of the cosmic time as A of T. So you need to replace T by something else and A by something else, both of them, that we can measure. So therefore we can measure distances. So let's try distances. Okay, like in the Hubble constant, we measure distance and redshifts, but we need to do better than local distances and redshifts. Okay, so what do? First of all, we define something called a conformal time. Okay, it's a distance really, because if you want it in physical terms, but people usually put C equals 1. So this is a conformal time. Why is it called conformal? Because we put it in an FRW metric, it becomes conformal. The escape factor comes out, becomes a conformal factor, and the space and time components are multiplied. Here, only the space component is multiplied. In conformal time, both of them are. So it's nice from a theoretical point of view. From a practical point of view, it's also nice because you can get something called the co-moving distance. This is the distance. This is actually the geodesic distance that we were plotting before. Where is it? Here. Shortcut. The geodesic distances on big circles on a sphere. For example, it's a sphere. but it's also geodesic distance for the other cases. And it's simply radial light rays. You put d omega equals 0, and a light ray moves on null geodesics. So this is a light ray moving on null geodesics, meaning ds is 0, emitted at some time t and absorbed at some time t naught. We are t naught, and it's emitted sometime in the past. Okay? Between something emitted at t and t naught, this is the co-moving distance between taken by simply putting this to 0 and this to 0 and defining that. So in intuitive terms, it's actually the distance between an object emitting at t and us, for example, at t naught, between observers that are close together, and it is stretched at every stage. Stretched at every stage, and if we use the convention a equals 1, it's in terms of our distances now. Nice for people who are used to economical inflation in Egypt. If you put an Egyptian pound in 1960, your father put it, or something, or your grandfather, and every year you put a pound, you don't get a pound nowadays. You get much more in the bank because there's 10% inflation. And it's actually like inflation. Economic inflation is d pound by dt proportional to the inflation. So it's like the inflation in Egypt is like inflation there. So it's like a disintegrate universe. Okay? So this is the money you get. You get much more than you put. Okay? In today's money. But it doesn't count. So it's a co-moving distance. If you wanted to transform it to some observer at a different time, you have to multiply by the scale factor of the observer. So for those who are interested in these things, I kept this. This is a bit theoretical. You know, there are horizons connected to this co-moving distance. If this thing converges from 0 to t now, which is the case, for example, in a static universe, or in universe expanding with matter and radiation and normal thing, then there's only so far you can see. For example, in a static universe, 10 giga-year-old, you'll see 10 giga-light years, you know, static. But it's not static, it's expanding, so you see 14 gigaparsec in 14 giga-years. So by chance, it's very close in parsec and light years, but it's okay? Because you stretch. This is not the case with inflation, for example, in dark energy. You can see infinite distances in the past, although they are stretched out, so they are dimmed. But there are things happening now that you cannot see. For example, a star explodes very far away. You'll never see it because it's inflated away. It's outside your horizon. It's an event horizon. So you'll never see that. Right? And you won't see the things in the past either, by the way, because they become very far and dim, you know, because everything is really inflated. And so you won't see much other than Andromeda and things that are self-gravitating with us, you know, if you are in a cosmological constant universe that keeps on going on. In the future, people won't see much at all. Okay? Now, of course, why is Andromeda? This is an important point from a conceptual point of view. Why isn't you will see Andromeda? Because the FRW metric is actually on scales further than the Andromeda and galaxies that are close to us. It's only on scale, it only applies on scales that are not in the room, not in the Milky Way, not in Andromeda and so on, between us, but on larger scales. Okay, and there's a point of why can we really do this averaging or not in VR that's contentious. Because we didn't start with the correct metric and then average it. We average first and start with the correct metric. So it doesn't apply to the room, because the room is not expanding. Neither is the galaxy. Okay. Okay. Now back to the boring observation. So So how do we want to start calculating the moving distance? So for our universe, we know, we suppose that there's only matter, normal matter, there is radiation, and there is the curvature that we have to put, because we don't know if there is curvature or not. And there is the cosmological constant. Omega is defined thus, by assuming a critical universe and dividing the current density by the critical universe. And this is the scale. Okay? This is a different scale. Okay, so this is just writing that in terms of dividing the actual density by the critical density. Now, the critical density is defined flat here. That's by definition. And these are different things. There's matter that expands as 1 over a cubed, because simply the mass is conserved and the volume increases as a cubed. Radiation, which also redshifts, so its energy, then energy of each photon decreases as a, and the number of photons per volume, expanding volume, decreases as a cubed, so it's a cubed times a to the 4th. This thing we saw is a squared, which is intuitive again, it's a Gaussian curvature, so it's a square. And this is a cosmological constant, so it's constant. At least the density is constant. Energy density, right? So we can integrate that if we know these things. Okay? You can also calculate the age of the universe if you know these things. And when people tell you it's 14 gigayear and so on, the age of the universe, this is one way they do it. So do it as an exercise. It's very simple. A trivial equation here. So if you know these numbers, you can know the age of the universe. That's how people know the age of the universe. Okay? So it's a very simple exercise that you can try. Okay? Now, as we said, we need, but first of all, we need A as a function of an observer. And we need DC as functions of the observers. We cannot measure co-moving distances either. So we're not doing much better than time. And we need something else. So redshift is relatively simple. The galaxies are going farther and farther apart. The wavelength of light is going towards the red, like sound goes towards longer wavelengths, base light goes to longer wavelengths as red. So you can measure that. And then you can define the following. Intuitively speaking, the light, it's not really a Doppler effect. It's light, it will be stretched with the expansion of the universe. So its lambda, it will increase with the scale factor. So if it's emitted at lambda 1 with T1, and lambda 2, or lambda now, or the reverse at T0, the wavelength will be the ratio of the two. The ratio of the wavelength will be the ratio of the scale factor. Because it will stretch as the scale factor, yes.
Question about how can we differ between creatures? Cosmological one and theoretical one.
And what?
Creatures الحين بتاعنا لو نزيد الفلوس.
No, you can't, but it's just that the special relativity becomes irrelevant at longer, at larger scale. Special relativity is for local inertial frames and so on. You're not in local, so it's not precise. It's precise only when you're in a local inertial frame. Okay, it's precise when the Newtonian equations are precise. In this sense. Okay, it's precise numerically when the Newtonian equations were precise. Inside Hubble speed, much less. Otherwise, you are not in local frames, and you cannot use local inertial frames. And you're not in special relativity. So, and then you'll have problem things moving faster or light with why? And why are they not changing mass? And so, no. So you could get it right, I guess, to some extent, but then you'll have problems. And by the way, observers do that, and they plot superluminant velocities. But they know that this is a representation. You'll find plots on the web with supernova things moving like 10 times the speed of light. Because they know this is just a parameterization. We'll find it. Right. So then you can define the reaction. This is Z. Very important cosmology. You define it as the relative change in London. And you can expand to linear order and find your Hubble constant. Linear order, huh? Linear, local. Can't go much further. They go to second and third order. People like Greece and so on, when they do this. But you can't go much further. At least not one. Z should be smaller than 1. Otherwise, CZ will be superluminous. Okay, but it's not a problem because these things are they're not locally. The expansion rate can become superluminal if you want, but not the local observer. Okay, so see if you could extrapolate that to Z equals James Webb, it will be 20 times the speed of light. That's wrong. So that's why you can't extrapolate. It's not linear, you'll see. So a bit more formal route to, right? If you want to do it properly, actually, that's how you should do it. That's why I put this. Then you'll say the conformal time between T0 and DC is invariant because I put delta plus T0 and delta plus T1. You can calculate it on that and you'll see it. The difference is invariant. Okay? So, and assuming that the wavelength, the frequency of light is far larger than any time scale of expansion, then the ratio between the Is there any questions? Questions? Comments? Yes. Yes, Ella? ما تدرسوش. There you go. So then you'll find again the time scales at T1 are related to the time scales of T2 by the ratio of the scale factors. Okay. So and you'll find the same relation we found intuitively. All right. Okay. So we have our model now fixed in terms of at least an important relation here, of course, is that, where is it? This, we now have the scale factor in terms of an observer, Z. Z is an observable thing in terms of wavelength, and Z is related to scale factors. And it's only the ratio that matters. As I said, you can put these absolute numbers even in megaparsec, if you want, or gigaparsec. It's the ratio. Okay. So we know everything about the scale factor now. Observation, if we can measure redshifts. Okay. So here we go. We're making progress. Now we need distances. There's two main ways of in cosmology. There are many others, but the two, well, not many, but there are a few others. But the two main ways are either angular diameter distance or luminosity distance. Angular diameter distance simply that if I have a small delta theta and I know the size of the object, for example, I can measure the distance to that object, which is called dA. دي الطريقة المقاولين بتلاقيهم قاعدين بالمنظار يعملوا بيه مساحات مش حاجة يعني exotic. Okay, not something exotic. Contractors in Egypt are always doing that. And when they have a large angle, they use sine. Okay, but small angle, this is okay. Luminosity distance is simply that light decreases, the power in light decreases as one of luminosity distance squared. The flux here of the luminosity or whatever. So if I have a light bulb that is 100 watts, I see it at 1 meter. At 10 meters, it appears to be 1 watt. 10 meters squared is 100 over 100 gives you 1. Okay? So that's as simple. So if I know that somebody put a light bulb at 1 meter to be 100 watt, and I see it, I measure it, I see only 1 watt coming, therefore I say that I am 10 meters away, or 9. Right? Now, angular diameter distance we're going to discuss next time with the cosmic microwave background and things like that, more in cosmological context. So this is for next time. It is simply the cosmological definition of r theta, the stuff we did before. Why r? It's because this is the Euclidean distance. Okay, this is the equivalent Euclidean distance on if it's a curved universe. And things will appear closer, okay? And that curve, positively curved, it will appear a bit further away if you're negative. So this is r theta, and this is my object. So if I know d, for example, for some reason, I know that this object is of a size whatever. And I can see the angular thing by measuring in the sky how much the object makes. Then I can know r. Okay? And there is a factor of 1 plus z because it is the proper, because there's cosmology here, and we need to use the proper length of the object at redshift 1 plus z, 1 over 1 plus z, which is a. It's multiplied by AOT because it's an object far away. Okay? So, because this is formally AR, okay? Because universe is expanding, right? So, simply, I have an angle in the sky, and if I somehow know that this object is, because there's one light kit, but it's not how it works. But for example, I know that this galaxy is this size because there's one light kit here. That's it. And I can see it at a much smaller size, angular size, small angular size than one nearby or one in the middle or things like that. Then I can calculate from the theta angle, and I know this one, I can calculate r. This is the, FRW coordinate that multiplies the angle. Okay? All right. So this is different from the geodesic distance that we've been calculating. The co-moving distance is that. This is the co-moving distance, and this is the angular diameter distance. But they're related. We know how to relate. So we're doing progress. Then there's the luminosity distance, which is more the subject of what we're talking about today. Supernova, mainly data, and so on. And this is a distance multiplying a squared angle, meaning d phi, the arc of a d phi and d theta. Okay, because luminosity is squared, it's r squared, the light goes as 1 over r squared. It's like gravity, so to speak. Okay, so it's multiplying a 2-dimensional angle here. Okay, that is d phi, the arc of phi and the arc of theta, 2 dimensions. Okay, so it's this. So it's theta and another one. It's an area. It's multiplying an area. Okay, angular, 2-dimensional area, and it's squared because it's multiple. So this is an area because our definition in the lab was this already. So we need a similar definition. Okay. There's 2 more things that we need. So, okay, so it's r1 over r squared. The r squared being the FRW coordinate. Okay. But there are 2 other things that we need to take into account when doing this. We didn't take them into account in the case of angular diameter distance because it's just angles, We don't care if the light lost energy when it came. We just care about size of it. But here we care about energy, about luminosity. So we need to take into account not simply that it was emitted when things were smaller. We don't care. A supernova is a point. We don't care the proper length of the supernova, what it was when it emitted, as in angular diameter distance. Here we care that the photons lost energy on the way. They became redshifted. So we need to take that into account. And when measuring the difference in energy emitted and the energy received here. We are receiving it here, the light has been diluted on the way coming. It has been diluted like that and like that. Note it's diluted Euclideanly, not on the curved thing. Because if you go through the geodesic thing, it doesn't dilute at all if you come here. It's diluted Euclidean. Okay, that's why we use R, not R chi. R small, not R chi. Okay? Not the geodesic distance, but the small FRW parameter or okay? Right? And less photons come, not less photons. In total, they will all come, of course. But the rate at which they come is smaller because we are moving in rate and so then it becomes dn is r times 1 plus z. So that this becomes squared. So this is squared because there's two effects. Okay? So this is the luminosity list. Right. So we got everything really that we need for this sort of exercise. We have, if we know these things, we can calculate DC. dH is simply the Hubble sphere, which we know if we know H naught. This is the Hubble sphere local, the Hubble sphere at A equals 1. And if we know H naught, we can calculate it. So we don't know these guys, but we'll try to make guesses about them. That's the whole point. If we know the redshifts to objects, that's easy. We calculate it. The redshift to the object. Relatively easy, not always. Yeah. If we're flat, then R is simply R chi. If we are positively curved, the FRW coordinate is like that, as we did yesterday. If it's negatively curved, then it's a shine. If it's hyperbolic, okay? Like we said, this is like a triangle more than 180. This is a triangle less than 180, and this is 180. This is more. This is less. Okay. So we can know DC, and R is also comes from, if we know omega naught, the total density, and DH, which DH we can know if we measure the Hubble constant. And if we somehow can know that, then we know R. And we can know DC from here. Okay? So we have everything really. To compare with that. I mean, we make a plot of these things observable. Okay? We observe luminosity distances simply by using if we have a standard candle and we observe a certain luminosity, then we can observe a luminosity distance. We need to compare it with a theoretical luminosity distance. What is the theoretical luminosity distance? It's from these things. We have a model that will depend on how much matter density and how much lambda density and how much curvature. I took the radiation out because these things are done usually for the late universe, when the radiation going 1/8⁴ density is like about 1,000 or more times less than the matter under cosmological constant. So I took the 1/4 of the radiation out. Okay? So this is our co-moving distance. We put it in this here to get the FRW parameter. So therefore, we can calculate theoretical distance. Because EL, I know R, and Z, I'm fine. How do I know R? From there. And I can measure the luminosity distance. If I know the real luminosity of a 100-watt light bulb, or a billion, whatever watt light bulb, I wanted to check it out for you, how much is this in watts, I forgot. Okay? A very high light bulb, and I see, let's say, it's 10 to the 10 watts, and I only see 1 watt, then I know it's like 10 to the 5 light years. Because it's squared. So I know that. If I know the supernova or whatever, exploding or some fire far away, and I know the intrinsic thing, and I see, let's say, 100 times less, I know I'm 10 times the distance, okay? Because it's square. And then I can make a plot of the distances, as we will see, and compare it with that. And what is that? Simply the Hubble constant and the matter density. And I can make a plot of that, of the theory. Matter density, omega, and so on, of lambda, and I make a plot of that using all these equations together. So that's the theory. I compare it with the light bulbs. So a brief interlude of how you do this in practice. How do we actually go about putting light bulbs in the sky? How do we make standard candles? They don't call them light bulbs. Probably because in Hubble's time and so on, there were more candles than light bulbs. So one way is simply the Ma'awlin again of the parallax. Remember in the very beginning when we said a parsec is like 1 arcsecond distance? The radius of the orbit of the Earth will look like 1 arcsecond at 1 parsec. You can also see stars moving between December and June, you know? They move a little bit because we are moving. Up to recently, there were very nearby stars that you could measure the Ma'awlin distance to. This is an angular diameter distance also, but a very elementary one, okay? Until recently, you could only measure very nearby stars. With Gaia, you can do the whole galaxy, but not very far galaxies. But when you do this for a certain galaxy, there are certain stars that you can calibrate with. That's how Hubble did that 100 years ago. Okay? You measure their distance with the parallax, the Shepherds, and they are pulsating stars. They light and darken. ينوروا ويطفوا يعني بالبلدي, roughly speaking, they go up and down. Okay? They have light curves that go up and down. Right? Things like that. Okay? The period correlates with the intrinsic luminosity. Luminous ones have different periods than non-luminous ones, right? Than less luminous ones. So the period correlates with the intensity. So if I find a Shepherd far away with a certain period, I can know its intrinsic luminosity by its standard candle. 1200 واط ولا 1000 واط ولا 10 واط ولا 30 واط ولا لمبة توفير وكده. Okay? So you can do that. So that's one step. And that's how they calibrate usually the supernova, but before that you will see that we have magnitudes here. I wanted to explain units of magnitude, but you can look it up on Wikipedia. Steven Weinberg also has a really nice historical introduction on his book on cosmology on magnitudes and so on. There's apparent magnitude, what you really see, absolute magnitude defined at 10 parsec. You have to define it somewhere, because if you really define it as a point, 1 over dl squared divergence. And nothing is really a point, other than maybe black holes. Well, even these have a horizon. So nothing is really a point. So luminosity distance has to be defined at some distance from the object, not like a point, because 1 over L squared will diverge as L goes, 1 over dl squared will diverge as dl goes to 0, so it doesn't make sense. So it's defined at 10 parsec from the source. And this is how you change from 10 parsec to whatever distance. Luminosity distance in terms of magnitude, defined like that. Magnitudes بيرجعوا لبطليموس بتاع اسكندرية. Okay? Magnitudes go back to, that's why they go the wrong way. Because he saw stars that are very high. He said these are number 1. أيام زمان. And 2 and 3, the reverse. So higher magnitude. So, okay? So it goes the other way than luminosity, okay? So there are ways of doing larger distances. There's something called the Tully-Fisher relation, which comes from the virial theorem we did in the first talk. I can see the rotation speed of the galaxy, and that correlates with it's a very tight relation. Nobody understands exactly why. Okay, that's another issue, but that's not our subject today. It's a very tight relation between absolute magnitude or luminosity going up, magnitude going by Lymos down. Okay, right? And the rotation speed. So if I can calibrate this to local galaxies and assume it's the same for higher redshift, further away galaxies, and I cannot measure the absolute magnitude, but I can measure I cannot measure the distance, so I don't know absolute magnitude, but I can measure the rotation velocity through Doppler shifts, so let's say hydrogen lines or something like that, can measure rotation velocity, I can read off the absolute magnitude from here. Okay? So that's one way of knowing distance in cosmology. But it's not as powerful, at least not yet. It could be with SKA, which is designed to probe hydrogen very sensitively. Something called the square kilometer array that they're building in South Africa and Australia. So this is a huge, I don't know how many thousands of radio telescopes. Maybe Mahmoud knows how many thousands? A lot. Many telescopes over a square kilometer, as the name suggests. Okay. It is what? How many in South Africa telescopes? Stage 1, say? And it's thousands, it's a lot. Okay, there are many stages. So this could be more powerful in the future, but for now, it's not. And I don't think it will be as powerful as a supernova anyway, because it goes to Z1 or 2. This thing is probably going further in the near future. Anyway, the supernova. The supernova is basically type 1a supernova are quite stable because they have a sort of ignition mechanism of two merging stars, reaching a critical mass and so on. So they seem to be stable from local universe to higher redshift universe, and the luminosity correlates with something called a stretching factor. So if you, for example, try to put these change the magnitude here, or the luminosity equivalently, change the magnitude of these things. This is going more negative because, as we said, the scale is reversed. And also change, in addition to the peak, the slope of this line. You can make them all the self-similarity relation. It's called the self-similarity relation in math. You can make them all yatatabtu. And Reset Al and others got Nobel Prizes for this thing after a lot of work. It started in 1998, and then it started even before that with a guy called Philip Penko also, who didn't get a Nobel Prize, but he was one of the pioneers. And Perlmutter also got a Nobel Prize and so on. So this, but it took like 10 years of calibration before people were sure that there's no reddening or that these guys were really standard candles in the sense that they don't change and the environment doesn't change around them and all sorts of complicated stuff. But in the end they got it, and so they could have standard candles. Now there are not enough of these in the Milky Way, for example, so you need to calibrate them with galaxies that have both Cepheids and supernova. That was another contentious point, and still contentious till today, especially in the Hubble tension thing and so on, and constant, which we will talk about at that time when we discuss the CMB. Okay, so you need Cepheids to calibrate the supernova. It's a distance ladder. You need first the parallax, then the Cepheids, then the supernova. And there are complaints that at every stage you can make errors and all, but they don't care. They got the Nobel Prize. Okay? So, right? I'm joking, of course. They care, actually, reason all the time, caring that he is right. Right now, no, he cares, even though he got the Nobel. He shouldn't. Yeah. Right. So, what else? So this is our thing. You plot your redshift with the luminosity distance that we measured because we have standard candles. We could measure the redshift of the supernova. That's relatively easy. Well, yeah, but also took some time to make sure that there's no reddening and all sorts of things, if I remember well. And we know the distance because we know how many watts the supernova is. Intrinsic. عارفين الوات بتاع اللمبة وعارفين المسافة لما بنقيس البتاع الضوء اللي جاي لنا شدته قد ايه. So you can do these are data of the supernova, and then these are our models for the luminosity distance that we calculate this way. In terms of redshift, I took the A out from the main equation of 2 slides before. This is, we took the A because now we know A is 1 plus Z. 1 over 1 plus Z, we know that now, so we can take the A out. A was a problem, we couldn't measure that, but we could measure Z. Okay, so we put Z in our equation here. Okay? We put Z in our equation. Yes, we put Z in this equation, we get DC, theoretically, if we put numbers here. I'll tell you about putting numbers. And we can put that from other measurements, as I say, of the jerk and the deceleration and the slopes and so on. If we want, we can leave it out. And we can make assumptions about these two guys. And then we're all set. R equals R sine, R capital sine chi. And chi is DC, this guy, over R capitals. And R capital we get if we have an assumption about these guys, and dH from the Hubble constant. Okay? So it's a closed system. There's nothing missing here. If you see anything missing, let me know. Theoretically, we are all set. We only need to make assumptions, of course, about omega m and omega lambda. Omega total is fixed by definition because it's a sum of both. Okay? Omega naught lambda nowadays and this. Okay? We need to make assumptions about that. We don't know. In fact, we want to find it. Okay? But everything else is really fixed in that, theoretically. Observation is also fixed. Here it is. So we need to know which model fits the data. Huh? Which model of our FRW, with the Friedman equation, fits this data. And this is, just to give you an idea what to expect, I did an expansion to first order in terms of omega m, which is the omega matter. And you see, the less omega m, you can see it from there, and the more omega matter, the more this dl has, the less omega matter here, the more this will start going as a square. The curve as a function of z will start curving to the top. Of course, you do this numerically, but I wanted to, you do all these things numerically, but I wanted to give you, like, for small z, smaller than 1, what do you expect? You expect if omega matter decreases. Okay, for flat, well, I'm assuming a flat universe, so there's no omega curvature. Okay, there's no curvature. So it's only omega matter and omega lambda, and it's flat. It's omega total. The omega is simply 1 minus omega n. Okay, so this is the omega lambda. You can see the more omega lambda you have, the more this curve will start being a parabola instead of a straight line. If we don't have anything here, this will be a straight line. You know, dH is a constant. It's the Hubble sphere. C over H naught. Okay, so this is a constant. So this is a line, but this is, the more of this stuff I have, the more of this thing, this bracket I have, the more it will behave as a parabola. So here it is. Things like that. This is just with the exponential only, so it's too much. And this is what was in my days, until 1998 or 2000, was called the standard CDM model. which means no cosmological constant, no exotic acceleration nowadays, and it is very bad fit, as you can see. Mahmoud likes these plots. This shows you the error. This is the best fit, which is the lambda CDM. You will hear about it. It used to be called the concordance, not anymore because it doesn't concord as well as people thought they concorded. Okay, concordance means tawafuk, more or less in Arabic. So, but there is now some tension, so it's not called concordance. It's called lambda CDM. It used to be called concordance because the fitting between these data and the CMB of Wednesday were perfect, or seemed to be perfect within the errors, but they diverged. Okay, they didn't diverge. It's not catastrophic, but it is quite serious, I would say. Right, so this is the standard CDM. It's very bad, and an open universe hyperbolic is very good. The best fit is the lambda CDM. It's the data quite well. Now, as you can see, these differences are very small, but they make very differences in errors. So this is why also by 2002, the WMAP, which is a cosmic microwave background satellite, people were saying the era of precision cosmology. Because it's precision. And these are already how many years old? At least 10 years, maybe. Well, it's tabulated in 2018 by these guys, but the data is probably older. There is new stuff which maybe Mahmoud and Walid know more about the latest. Maybe you can tell them a bit about the latest supernova and they're interested. They're doing the lambda CDM part. They should know a bit about this stuff. I'll talk to them about turbulence. I don't want to talk about that. Okay. So, right? So very highly precise. So this is the lambda CDM currently favored model. Now there is all sorts of discussion whether this was a big discovery because it's like a cosmological constant should be 10 to the 100 according to fundamental theory, or at least 10 to the 50 or number what, if you have supersymmetry or something like that. And you find it of order 1 here, so it's in these units, so it's a huge, and also what is it? Why is it accelerating? Now, you've probably all heard of Einstein and his blunder. He put the cosmological constant to make the universe static, but obviously he didn't think about it very carefully because he was desperate. Probably, I mean, this is Einstein. It's not like because he's not smart, but it's because he's desperate. He wanted that. Because obviously it can't work because the equations are those of a brick thrown up. You cannot have a brick thrown up standing. It has to go either up or down. It's big, it can't stand. But you can make it stand, but it will not be stable. And his solution is static, it's correct, there's nothing wrong with it, but it's unstable. So now, so he wanted to do, instead of recollapsing universe, to make it marginally stable by putting this anti-gravity, so to speak, by putting this, repulsive gravity. As I said, this is negative pressure. Negative pressure produces gravity that is repulsive. Positive pressure is gravity that is attractive. Because positive pressure, and when you put it in the field equation, it behaves like a mass. So it's attractive. It's not like a hydrodynamic pressure of Laplacian. It's not like a pressure gradient. It's a pressure that is a mass equivalent that is fundamentally relativistic. It's not hydrodynamic pressure of the sort we may speak about in the afternoon or on Wednesday when we talk about particle structure and the CMB. No, this is a pressure. It has to be relativistic because if we remember again, this is an important point. I mean, remember again our equation. Where was it? Our fundamental equation. Where is our fundamental equation? Not this one, the one that has pressure. Where is it? This one. It is 3p over c squared, and p is like rho v squared for particles. So if v is less than c, much less than c, this compared to rho is very small. This is a good, so it has to be relativistic. It's a mass equivalent. Okay? And it has to be negative. When it's negative, negative enough, this is positive. And this is positive. So that's what we mean by an accelerating universe. Okay? One where the pressure is negative enough to for this bracket to be negative. 3p minus rho over c squared, 3p over c squared is bigger. The absolute value of 3, p is negative, and the absolute value of 3p over c squared is bigger than rho. Okay, so that's what you need. And then this thing, instead of becoming a deceleration negative, طوبة بتقع. الطوبة بقى في حاجة بتخليها really accelerate. This is not the Atuba equation anymore. That's why that's another reason the Newtonian approximation that we're using is lacking. It doesn't take photons or neutrinos into account, at least relativistic neutrinos, and it doesn't take exotica of this sort into account at all. There's nothing in Newtonian gravity that has a negative mass equivalent, so to speak. Okay? Right, so where is our nice spot? Yes. So it is this effect. That's important. So this is like with only lambda and no matter. Like I said, it would do like a parabola, but it's too much. In fact, we have lambda 0.7 and omega matter 0.0. It wasn't always like that, because omega matter, the matter, when it was compressed, its density increased as the 1 over volume, and the volume decreases with time. So it's at earlier time when A was, let's say, 0.1, or let's say when it was 10 to the minus 3 at redshift 1000 at the CMB, which we'll discuss on Wednesday, this thing was 10 to the 9. This guy. So another thing is, why is it suddenly a cosmological constant or whatever dark energy now? Okay? Nobody knows. And I think we're more or less done. And nobody knows also if it's really a cosmological constant or it varies a bit. Is this equation of state here for a cosmological constant? As we mentioned, you need an equation of state. Where is it? Equation of state. -1. Right? How do you know it's exactly -1, not like varies with time and appears to be -1? This is one of the major questions that are being milled, both theoretically and observation. Theoretically, like there are thousands of models or whatever. There's a lot of them. Yeah, probably at least in the hundreds, I would guess. Certainly more than 50. Okay. Observation is going to become really exciting with new supernova data and with new data from other sources, large-scale structure, lensing, and so on, that we have time to discuss, and galaxies, of course, that we'll discuss on Wednesday or Thursday. So finally, this is just the coming talks, and there'll be one on Wednesday and maybe 1.5, 2 on Thursday, depending on how far you want to go on this. Okay? Because it will be the closing. So I'll give a talk. We can stop it at any time you say this is enough. I don't want to hear any more of this. Okay. I designed it this way so that it's easy going. Okay. So next talks, the 3 next talks will start from the CMB here, this fire in the sky, of course, color coded for this is not, you don't see it like that, but it's color coded like a fire for advertisement purposes, and how the galaxy is formed and how they're distributed and their types and so on. So this will be on Wednesday, and if we arrive to that, it will be great. Okay, thanks. Any questions? I've got the supernova come what? I wanted to look it up, but I'm upset. How many watts is a supernova? You know how many watts? You may know how many watts is a supernova. At the peak. Call it 10 to the 30.